G'day chemists. In this video, we're going to look at rates of reaction, how we calculate them, and so on for our kinematics component of our course. Alright, so today we're going to learn about, we're going to learn to express the rate of reaction as a change in concentration or mass or volume over a unit of time, usually seconds, for a particular reactant or product. We're also going to look at calculating the rates of reactions using tangents of graphs and quantitative data that's given to us. So that'll be, on your y-axis, usually you'll have concentration, mass, or volume, and on your x-axis you'll have time. Alrighty, so rate of reaction. What is it? Let's have a quick look. So the rate of reaction is the change in concentration, again can also be mass or volume, of either a reactant or a product over a period of time. And let's have a look at this experiment we have over here. Here we have an example of hydrochloric acid with zinc, metal zinc added to it, which is going to give us zinc plus hydrochloric acid goes to zinc chloride plus zinc chloride plus hydrogen gas. And what we'll be looking at there will be the mass of hydrogen gas produced. And we'll be able to measure this because the mass of the overall vessel will decrease, which gives us the amount of mass of hydrogen gas which has been produced, because that will release off into the atmosphere. So as it's a rate, it's mathematically synonymous with velocity and speed, and that's kind of cool. And sometimes you'll see it written with a V, but that fun little sort of cursive V that they use in physics courses. But we'll use the word rate usually in our course. But I mean, either way, you'll see both, and they're fine. So yeah, so here we'll have, again, they weigh it at the beginning, and then they will drop in some zinc into the hydrochloric acid. They'll get that weight real quick, and then they will record at regular intervals. It could be like, every 2 seconds, whatever. It could be every 30 seconds, how much the mass decreases. Now, what I will say is in, for example, our IB course, as senior chemists, there are a couple of things we'd do differently. We would have some cotton, for example, sitting up here with the goal of stopping dust from stuff coming in, because it'll allow the hydrochloric acid to leave still. So that's just like an extra control to make sure everything's okay. And we would probably do it using a data logger to make sure that, we're getting a really accurate read over time. All right. So another fun thing about this, and we'll have a look at the formula in a second, is that it's done with absolute values of concentration or mass or volume, doesn't matter. And what we mean by absolute values, that's a mathematical term, meaning that it doesn't have a sign, or it's always positive, basically. So just to allow, an easier expression of that rate of reaction. So for example, if we were just going back to our synonymous with speed, you could be, forward 60 kilometers an hour or backward 60 kilometers an hour, but we would still call it 60 kilometers an hour, and that's how we treat it here as well. All right, so let's have a look at what this looks like mathematically. We'll have a look at graphs and stuff in a second, but we'll start off with raw quantitative data. So we have our equation. Rate equals the absolute change in concentration over the change in time. Okay, so how long it's been going for. Now again, it's an absolute value. That's what these straight up and down bars mean. And that means that it's always positive, and just makes our maths a bit easier, and it doesn't affect it in any negative way. But this can also be absolute change in mass, or absolute change in volume. So our previous example that we just looked at would be a change in mass, and the mass would be going down. But because we put those absolute bars in there, we're going to treat it as a positive change. And we have units. So our units are moles per decimeter cubed per second if we're doing it as a concentration value. If we're doing it as a volume, it's going to be centimeters cubed per second, or decimeters cubed per second, or per minute if you want, but whatever. But that's your rates there. If we're doing mass, it's going to be grams per second. Again, there might be more important units, like more appropriate, units to use, but that's usually where we'll start. So let's have a quick look at how we do a calculation. So here we have the concentration of silver ions reacting over time. We're measuring the concentration down here, and we have our time. So let's have a look at how we would do this. So we would look at this for like the first minute, for example, which is quite a long period of time, to be honest, but we'll go with that. So absolute concentration over change in time. So that would be 3 moles per decimeter cubed minus 2.73, because we've got our final volume and our N1, right? We're going for the absolute, over 60 seconds. So we end up with like 0.27 moles per decimeter cubed over 60 seconds. Just have a look here. See how that's a decimeter cubed like that, but it's about to have that negative put in front because, well, actually it should have it there now. It should be negative there, moles per decimeter cubed. Moles per decimeter cubed. That should have a little negative sign there. We'll fix that up in a sec. And that gives us 0.0045 moles per decimeter cubed per second. All right, so that's how we do it. That's that simple. We just plug the values in, use this equation. Those are our units. Donezo. Now, this is an average over that 60 seconds because the rate of reaction changes. The preferred way to measure the rate of reaction is to use a tangent. And we can do that as the initial rate of reaction, which is our perfect spot to do it. We like that one. And we do that because that's the conditions that we control. As we increase our time, the reaction will release energy or absorb energy from the environment. The concentration will change. So our conditions become less controlled, whereas our preferred way to measure it is the instantaneous initial rate of reaction. Now, the instantaneous rate, if you look at this graph, you'll notice that the graph it's not a straight line at any point. Okay? It might plateau out further down beyond if we extrapolate it, but it's not a straight line. So we don't want to use the average because that'll give us some dodgy data. We use tangents to get our instantaneous rate. So again, we draw a tangent against that graph. Boom, boom, either one. And then because it's changing concentration, which is the rise, divided by the change in time, which is our run, we can just use the gradient equation, or gradient formula, which is rise over run. So you draw a straight line as a tangent using your ruler down here, and then you measure this number, okay? In this case, it would be, what's that, 0.04, and then you divide it by the time, which in this case was 200 seconds. So your initial and instantaneous rate of reaction would be 0.06 divided by 200. So that's how we do it. Now, the rate of reaction will not be necessarily the same for all reactants or products in a reaction, and that makes sense if you think about it, right? It's proportional to the equation coefficients. So the example I always like to go to, because it's a fun equation, it's got lots of cool stuff happening, it's really important in our high school chemistry in particular, is the Haber equation. So let's have a look at a graph for it. So this is the rate of reaction, right? We start off with 0 hydrogen gas and nitrogen gas. We start off with a little bit of ammonia, and we see that as the ammonia is used up, the hydrogen and nitrogen are produced. This is the Haber equation. It's drawn backwards to how it's starting here, but that's just because that's the way you'll usually see it. And what you'll notice is if we look at ammonia here, its rate of reaction is about 2. And if we look at hydrogen here, its rate of reaction is about 3. And then we slide over here. Here's our ammonia, which is a coefficient of 2. And the hydrogen has a coefficient of 3. Now, that doesn't mean that they're always going to be equal on that front. Like, it's not like it will always be like 3 and 2, but that ratio stays the same. That's the important part there, is the ratio is what's keeping it, proportional to the equation. And this makes sense because for every mole of nitrogen produced, we need to make 3 moles of hydrogen. And to do that, we need to use 2 moles of ammonia. And that's why it's always proportionate. Or proportional. So I hope that made a lot of sense. If you have any questions, put them in the comments below. If you have any feedback, put them in the comments below. I'm trying to speak a bit slower than I usually do. And we'll get back to you as soon as we can. Thank you for watching, and we'll catch you next time. Bye now.